A good example of the trig functions being applied in a physical system is a mass spring system. We're going to expect to see oscillation, and we can tailor it so that we don't have decay. And I'll show you an example of when we do have decay, but it's easier to look at least initially, without any decay. So here we have our spring. We have some kind of mass at the end of the spring, and we can either compress it or we can put it in tension and then release, right? So I will talk pretty high level of the physics of the system, and I want you to see how changing some parameters affect the response of the system as we track the location of the block across time. So here is our mass spring system at equilibrium. So we're going to define that as 0 meters. It's the mass is stationary. There's no force applied to it. I can compress it. If I compress it, then we can say we have some positive x value, let's say 3 meters, or I can pull it in tension or extend it like we have here and say then we have a negative value, negative 3 meters. So we're going to take a look at the position, the x position of this block over time under a variety of different initial conditions. I'm going to set up the physics, the equations setting up here, and I'm going to show you the velocity and acceleration solutions as well. And what we're going to try to solve for is x of t, the position over time of this block. And over the course of this video, we're going to take a look at different initial conditions and see how that affects that position solution. There's a number of steps here that I'm not going to fully explain because the physics and engineering side of this go beyond just one video, and I want to focus on looking at the effects of initial conditions on a system that's oscillating and tie it back to the things that we're talking about in terms of just generic sine and cosine graphs that we see in the oscillation curve. Right. So here we have the general equation. On the left side here, we have mass times acceleration. X double dot is our acceleration term. That's the force onto the block. Plus kx, this is the spring force, right? K is a spring constant, x is the position. So the force that the spring applies on the block is dependent on the displacement from equilibrium. That's why it's kx. K is our spring constant. We'll define that in a second. This is equal to the applied force, F of t. We're going to say for this video that this is equal to 0. So there's no external force. We can have a different initial condition, but we're not going to apply a force. And so we're going to set that equal to 0. So that's my general equation. My initial condition for this baseline example is that I have the spring compressed. So there's a displacement of 3 meters from the equilibrium point. And x dot is our velocity. So initial velocity we say is equal to 0. So we're just going to hold this block and then let it go at time t equals 0. So initially there's no velocity. Spring constant is 100 Newton meters, and the block of our mass, right, this black square, is 4 kilograms. Right, and so if I divide by my general equation by mass, by mass, I get the acceleration plus k over m times position is equal to 0. And so we're going to use this equation, and we're going to derive the position, the velocity, and acceleration. We're going to use these 3 forms. So the position, a sine omega t plus b cosine omega t, has 3 unknowns: the coefficient a, coefficient b, and omega, which we know it will affect our frequency and period. Assume that you know this. Assume that you recognize the oscillation behavior, but you don't know the amplitude and you don't know the period, and that's what we're going to solve. If you've not taken calculus, you might not know the derivative forms, but position, the derivative of position is velocity, so the rate of change of position is velocity. That's how this equation was formed. the rate change of velocity is acceleration. That's how this equation was formed. Don't worry too much about how these are derived. You can, for the sake of this video and purpose of what we're trying to demonstrate, assume this and the general equation to be given to you, right? So these are the known equations, and you need to solve for A, omega, and B given the initial conditions. And so that's what we're going to do now. So first we're going to use our initial condition of the position. So x equals 3 meters at t equals 0. So at t equals 0, I'll plug into this first equation right here. So A sine omega times 0, 0, plus B cosine omega times 0, which is 0. And that's going to equal 3. Sine of 0 is what? Is 0. Cosine of 0 is 1. So this would just be B. B is equal to 3. B is equal to 3 meters, that initial condition, right? So we have a second initial condition. This is the initial condition of the velocity term. So you can plug in my values for this equation here. So at t equals 0, omega t would be 0. So cosine 0 times a omega minus b omega. Well, b is 3, so I could plug in 3 omega times sine 0. Sine 0 is 0. Like I said earlier, cosine 0 is 1. So we get a omega equals 0. So a is equal to 0. Okay. If you forget what sine and cosine are at 0, you could draw that unit circle. Remember, sine is the y value of that unit circle. Cosine is that x value of that unit circle along that positive x-axis. Okay. So I've used both of my initial conditions. Now I want to use the acceleration form. Okay, I can plug in a and b into my general equation. I still don't know omega, but if I plug it in, I get x of t. My position equation does not have the sine term. That drops out because a is equal to 0. So I get 3 cosine omega t, and I need to figure out what omega is. So I can plug x double dot and x, the acceleration and position, into this equation. So that's what this is showing here. So the acceleration is negative a omega squared sine omega t. Well, that's just 0 because a is equal to 0, minus b omega squared cosine omega t. So that's this first term down here, minus b, which is 3 omega squared cosine omega t, plus k over m times x. There's my k over m. This is my x, 3 cosine omega t. So I have a 3 cosine omega t on both of these terms. This is equal to 0, so I could drop that 3 cosine omega t. And I'm just left with negative omega squared plus k over m is equal to 0. Or omega squared equals k over m. Take the square root of both sides. Omega is equal to square root k over m. Now I have all three. I have a, b, and omega. So I've solved for this problem already. So I plug in 3 cosine square root k over m times t. K is 100 Newton meters. M, my block mass is 4 kilograms. So that's 100 over 4 is 25. Square root of 25 is 5. So I get 3 cosine 5t. So here's my graph. So this vertical axis is my position, x. This horizontal axis is my time scale, t, time. And here's the oscillation. We start off at our amplitude at 3 meters. It's fully compressed, so it comes back, passes the equilibrium point, and then continues, right? So we can see the frequency, the period. We can calculate all that like we did before. Let's change some things about the initial condition and see how this graph changes. I'm gonna show the full derivation, but I'm not gonna go through that process again. I'm just going to highlight in red text the things that change by changing this initial condition. So this will be our baseline derivation, and I'll have this baseline graph there as well as a reference point for comparison. So the change here, so this is our baseline graph. The change here is I'm going to change the position from x equals 3 meters to x equals negative 3 meters for my initial condition. So instead of fully compressing and then releasing the block, I am fully extending, right? So I'm extending this. This is my equilibrium location. So I'm extending it down to negative 3 meters. Okay, what do you think the graph will look like? I show you the full derivation so you see the solution. But what do you think the graph will look like relative to this one? All right, keep that in your mind. So all of this initial setup is exactly the same. The difference shows up when we plug in this initial condition term. That's this equation right here. So -3 is equal to a sine 0 plus b cos 0, which is just b is equal to -3. So that's different. In this case here, b was equal to +3. So now -3 gets plugged into your velocity endpoint. That didn't make a difference. A is still equals 0. So here's my equation for x of t, but omega is still unknown. I use the general equation x double dot plus k over m, x is equal to 0, plug in. It doesn't make any effects because the frequency is still just square root k over m. Okay, so my only change through this equation is the amplitude. It went from a +3 to a -3. So basically, I'm just flipping this graph across that x-axis. And that makes complete sense, right? The frequency you don't expect to change, the period you don't expect to change, the amplitude, in fact, you don't expect to change other than the fact that you're mirroring across this x-axis. So you start at -3 and you rise up, right? You come back towards the equilibrium point until you get fully compressed up here. So you can think about this as mirroring. You can also think about this as a phase shift or a delay component. But that's the effect of that positional initial condition change. Let's take a look at another initial condition change. Actually, before I change in the next initial condition, let's see what happens if I change the mass of the system. Position, velocity, and acceleration equations are still the same. The solving for A and B constants, still the same, no effect by the mass. In fact, the mass only shows up at the end when we're defining our frequency, right? So instead of 100 Newton meters for a spring constant and a mass of 4 kilograms, decrease the mass to 1 kilogram. So now 100 divided by 1, square root of that is 10. So my frequency is now, my omega term is 10t, right? Or is 10, right? So inside cosine will be 10t. So you increase your frequency, right? It was this baseline solution was 3 cosine 5t. Here we have 3 cosine 10t. We could have changed our spring constant, but this is to show, right? Our amplitude did not change, our initial starting point did not change, but the frequency and the period response changed. How did it change? By changing the mass. I can do the same thing by changing the spring constant. So it's important to know what physical properties that we can change and how you expect your final solution to change. All right, so the next, we're going to take a look at what happens if I change the initial condition for the velocity term. Okay, so now if I changed my initial condition of the velocity, so the baseline, the velocity was 0 meters per second. If we say at 3 meters, the velocity starting out already at t equals 0 is 5 meters per second. So it's continually compressing. How would this affect my graph? I would not be decaying like this baseline response is showing. I would continue to rise. But how much will it rise? So that's what we're going to look at here. So we're still saying the initial position is at 3 meters. We're just changing the initial velocity. So we use the same general equation, position, velocity, and acceleration. All that still stays the same. Okay. We use the same solver for the initial position, right? So we still get b is equal to 3, just like on our baseline solution. For our velocity, now it's different. Now, so I put in red text the terms that are different from the baseline derivation. So 5 meters per second is equal to the velocity at t equals 0. So a omega cosine 0 minus b omega or 3 omega times sine of 0. So this term drops out, the sine term drops out, cosine 0 is 1, so a omega is equal to 5. I'm trying to solve for a, so I get a is equal to 5 over omega. Okay, so my general solution is 5 over omega sine omega t plus 3 cosine omega t, and I still need to solve for omega. So to do that, we do the same step we did earlier. We plug in our acceleration and position terms into my general equation, x double dot plus k over m x equal to 0. So the first square bracket is this acceleration term, x double dot. That's negative a omega squared sine omega t minus b omega squared cosine omega t. A is 5 over omega, right there. B is 3. And so this term, sine omega t term, is new. A was equal to 0 in this baseline case. So that term is new. Then we say plus k over m times x. K over m times position. That's this term right here, right? So just plug that in here. And what we see is we have 2 sine omega t terms, right there and right there. We have 2 cosine omega t terms, right there and right there. And so we want to combine them. So sine omega t times 5 over omega, that's my common a, times k over m minus omega squared, right? That's this first sine omega t term. The cosine omega t term, we have 3 times a quantity k over m minus omega squared, right? Times cosine omega t. Now, maybe it feels like I'm skipping steps. Write it out yourself if you feel like that will be helpful, right? So this is all equal to 0 at all times. So I can't take into account the sine omega t, cosine omega t. What I can factor out of this is k over m minus omega squared. That's common. So that term's got to be equal to 0. If that term is equal to 0, then we see the same frequencies actually showing up as we had from the previous cases, the baseline case, right? So omega squared is equal to k over m. So omega is equal to square root k over m. And it makes sense that your frequency will be the same. There might be, what we'll see is that there is a phase shift if you're just recognizing the peaks as that. But let's see what this will look like. So I have omega, I have a, and I have b. So I'll plug in all of these into this general equation. So I got 5 over omega, or times square root m over k, sine omega, so square root k over mt, plus 3 cosine square root k over mt, right? That's my omega t term. Plug in my values, I get sine 5t plus 3 cosine 5t. Right, so the 5 here and the square root 1 over omega cancel out, right? So 4 over 100 gives me 1 over 25. Square root of 1 over 25 is 1 over 5. So that's why that cancels out. So I get 1 times sine 5t plus 3 cosine 5t. Makes sense that both will have the same frequency. There is a combination of phase shifts, and we see that effect here, right? So this is my position solution for this case. If you look at the peak right here, it's not starting at a peak at t equals 0. It rises for a bit and then drops. So there's a small change in your amplitude. It's not exactly just 1 plus 3 because cosine and sine obviously are phase shift from each other. So there is not a perfect addition, right? It's not like if I said 1 cosine 5t plus 3 cosine 5t, then that would be a direct amplitude change. So recognizing that having an initial velocity that's non-zero will add a phase shift to my system and change my final amplitude. That's important to know. All right, here, so we're gonna show all the graphs all on top of each other so we can make some general comparisons and observations. Here's our baseline graph where we had a 3 meter initial condition, initial compression, no initial velocity, and the mass was 4 kilograms, right? Then here are all the other conditions thrown on top of it, right? In blue, we changed the starting position. to be an extension of 3 meters. So the starting position basically mirrored the graph. So we start at -3, and then it goes past the equilibrium point, and then to a compression of 3 meters. In orange, we changed the frequency of the system by changing the block mass, so the omega term changed. And so you can see we start at the same starting point as the baseline shown in red here, but I have an extra cycle for every cycle that this red curve is showing here, because we go from omega 5 to omega of 10. So the period is cut in half, right? Frequency is doubled. So that's reflected here too. And then in green, we have a change in the initial velocity. So a non-zero, not a positive non-zero initial velocity. So that's the introduction of this sine 5t term. So there's a small change in your amplitude, as we can see here, by that velocity. And then there's a small shift in phase shift from this, right? So all these examples, the oscillations are going to happen and continue forever and ever, right? So this x-axis, this horizontal axis, is my time axis. So it's going to keep going forever. I'm not going to show you the derivation, but if you have any kind of decay, the decay can come from some kind of air resistance. It can come from the spring having friction in it. It could be a secondary component, a damping component being added to the system. We can do the derivation. I'm not going to do it here, but the solution that comes from it is just a simple decay exponential. So I want to show you what that looks like in comparison to this baseline red graph. So again, here's the baseline red graph, 3 cosine 5t. And the additional 3 graphs, blue, orange, and green, are various decays. So we take the baseline solution, 3 cosine 5t, and we multiply it by different exponential, e to the negative some coefficient times t. So this exponential term forces a decay, but it's different depending on what this coefficient value is. So in blue, I put a small decay, a larger one in orange, and an even larger one in green. And so we can see the effects of this, right? So -0.5, -2, and -10. Now for the case of this problem, it's the relative change that I'm trying to demonstrate. So in blue, that's the smallest decay. So you can think about it this way. If I put a value of 0, this exponential will basically be equal to 1, which is essentially your red graph here. So we're going from exponential coefficient of 0 here, -0.5, -2, and -10. So you can think about it from that perspective of here in red is basically 0, a small decay component shown in blue, right? So you can see the frequency, the period, locations, no phase shift from the baseline, but each it's slowly decaying, right? So each amplitude at the trough or the peak is going to get smaller and smaller, and I can extend this, and you will see that in orange it will slowly become that it will decay even more quickly. And then there's a point where we say we pass the we consider over damped, where you don't even see these oscillations. It's so damped that basically it drops, and you can change how fast it drops, but it drops and then it just basically flatlines through the system. And I can increase this value and it's going to drop even more dramatically. And you can use that concept as another point, right? So oscillation with decay is a very important study in engineering and physics. How much you want your decay, what are the constraints of your physical system, all of that can come into play too. So we can look at that, not in this series, but just keep in the back of your mind that oscillation you can add different components to it, right? We can turn this oscillation so it's combined with a linear equation. And so it has oscillation, but there's also a change in height of the baseline over time. So a lot of things we can play with, but you have to understand the fundamentals. That's why I want to show you this basic application.